Hey everyone. In this video, I'm going to talk about how to specify priors in logit models using RStan ARM, and in particularly how they can help us overcome some of the issues that we can encounter if we use logistic regression in a classic frequentist framework. Okay, we kind of started this discussion last week already when we kind of try to answer this question of why we're using or why we want to use stan underscore GLM instead of the classic base R GLM function when we're estimating logistic regression models. Okay, and the example that I showed you there was one issue of perfect separation, and this kind of problem occurs if one predictor or a set of predictors, the linear combination of a set of predictors, basically perfectly determines whether the outcome measure is either a 0 or a 1, right? So in our case, last week we had we examined predictors of voting behavior, and we had one election where being African American perfectly predicted, at least in the sample that we looked at, perfectly predicted vote for the Democratic candidate, and that ultimately in the basic maximum likelihood framework, or estimating logistic regressions using maximum likelihood, ultimately results in a coefficient that is essentially infinity or minus infinity, depending on whether you're perfectly predicting a 0 or perfectly predicting a 1. Okay, and so that's a problem in the classic frequentist framework when we're using logistic regression. And ultimately, the way we can kind of get around this problem using STAN and using the Bayesian framework is that we incorporate priors. And these priors, when we use default priors, are just weakly informative priors, right? So we don't incorporate any theoretical, information about what we believe the coefficient for a certain predictor should be. But what we do is we specify a range of kind of reasonable values that we would expect for a model predicting turnout, okay? Or for any kind of logistic regression model with a specific, set of predictors that have a certain range, a certain distribution, and so on, okay? And so basically, if we encounter an issue such as perfect separation, then even these weakly informative priors help us kind of keep the coefficients in a reasonable range and therefore avoid issues such as perfect separation and others, okay? And so now we can kind of continue this conversation and this discussion of why the Bayesian framework can actually be extremely useful with logistic regression. And here we're going to look at not only the issue of perfect separation, but in general the issue of sample sizes and what happens with small sample sizes, okay? And if you're interested to kind of dive more into this issue, I definitely recommend also checking out the Rainy paper that I uploaded on Canvas as well, okay? So the way we're going to look at this in this quick video is we will define a function that directly simulates some toy data that we're going to look at with a true, for us, known data generating process. And then we will run both GLM and stan GLM, and we will just compare the results, right? And this is just a simple simulation exercise that we're going to go through that is also discussed in a very similar way with slightly different code, but the structurally very similar in the textbook as well. So make sure to check that out as well. Okay. So the function that we're defining here is called stan base underscore sim. It's a function which has 3 inputs. Okay. The first input is just the sample size n. Okay. The second input is our true intercept, right? The true has the true data generating process. There's an intercept, and that intercept has a value of -2. And then we have a true slope coefficient for one independent variable, and that slope coefficient has a true underlying value of 0.8. And our goal, of course, is to estimate both the intercept and the slope coefficient, okay? We have a set of inputs, so an independent variable, x, which is just drawn from a random, from a uniform distribution that ranges from -1 to 1. And of course, the number of draws from that uniform distribution is equal to n. Okay, and we're going to set that as part of the function. Then we basically have an underlying, this is kind of specified in this latent variable context. We have an underlying z variable which follows a logistic distribution. So these are random draws from a logistic distribution of again size n. The average of that logistic distribution is determined by our systematic component. That's a plus b times x. Okay, so this is the basic univariate or bivariate specification with one intercept and one slope for one independent variable, and we have an variance or scale of 1. Okay, and then of course this latent variable is not what we actually observe. What we only observe is the observation mechanism, where we actually observe either a 0 or a 1, right? And so here with this latent variable framework, we basically observe a 1 whenever our latent variable is larger than 0, and we observe a 0 if the latent variable is smaller than 0, okay? So ultimately the only variable that we have as an outcome measure is y, and z is basically unobserved, okay? So our fake data, as I mentioned, then just consists of two variables, one our outcome y and our predictor x, okay? That's the basic framework within the function, and then we fit our GLM with y regressed on x, same with the stan underscore GLM. And the only difference here is that with our stan GLM function, we specify a prior distribution for our slope coefficient. Okay, so this is just the prior, not for the intercept, but just for the slope. For the intercept, we just use the default prior, and that prior is follows a normal distribution with mean 0.5 and standard deviation 0.5. Okay, and then the last part of this function is just basically combining the output of the GLM fit and the output from the stan fit into one list, and then returning that list. And we're going to use that list with varying sample sizes. Okay, so let's look at the results in the first step by just simulating now data with a sample size of 1,000. So 1,000 observations in our data, and we're running with this data generating process where, as we said, a is equal to -2 and b is equal to 0.8. And our goal is to just estimate those coefficients, okay? If we have a sample size of 1,000, of course, you know, basically all the large sample asymptotic properties, central limit theorem, and so on, they all hold. So, and the sample size is fairly large. So our, basically our conventional frequentist logistic regression should give us a pretty good result that is close to the true data generating process, but also our stan model should give us results that are close to the true values, because with such a large sample size, of course, the priors ultimately will not really play a big role. Okay, they will not influence. They will basically there's more precision in the likelihood than there is in the prior, basically. And so our estimates in the Bayesian model are also, you know, mostly determined by the data, by the likelihood. Okay. So the way we can kind of explore these results is just by running this function that we just defined with n being equal to 1,000, and we can look at two different outputs, which is again the basic GLM function and the stan function. And looking at the basic base R GLM function, we see that our point estimates are pretty close to the true underlying data generating process. For our intercept, we have minus 2.08, excuse me, and then for our slope, we have 0.97. Okay, so that's pretty close to the 0.8 value that we kind of set in the true data generating process. Okay, so that looks pretty good. Our results are pretty consistent and also fairly precise. The standard errors here are 0.1 and 0.18. Okay, And the results are very similar if we use Stan. If we run the same model with Stan, or if we just look at the output of our Stan model, again, we have an intercept of -2 and a slope coefficient, or a coefficient for our independent or for our predictor x of 0.915. So very close to the result that we received in the classical frequentist framework. Okay. So how do things look if we reduce the sample size? Now we basically go through exactly the same exercise, but instead of having a data set of size 1,000 observations, we now have 100 observations. Okay, all we have to do is change that argument in our base sim function, and then look at the outputs just the same way. Okay. And one thing that we see here is that at least when it comes to the intercept, the estimate, the point estimate is still fairly close to our true value, which was -2 for the intercept. But now we see a slightly larger coefficient for x, right? Remember the true data generating process, b was set to be equal to 0.8, and now we have a coefficient of 1.2, which is still which is less precise. Obviously, it's still statistically significant from basic frequentist perspective, but it's certainly larger than the actual true value, and this is because logistic regression with small sample sizes tends to be biased and tends to have inflated coefficients. Okay, 100 is of course still not an extremely small sample, but we already see those effects. Okay. Compared to that, when we look at the results for our Bayesian model, where we were able to specify prior information to kind of give some indication of the reasonable range that we expect for our slope coefficient, we see that our parameter is actually still very close to our true data generating process of 0.8. Okay, and note here that our prior was not centered directly at the true value, right? We didn't set the prior to be equal to 0.8, which is the true value that we set in our simulation. We just set a range that was kind of reasonable to expect, where that was consistent with the data, right? The prior mean was 0.5, and there was a variance of 0.5 as well. Okay. So basically, despite the fact that we have a smaller sample size, we still get a better estimate for for example, prediction and so on, because the estimates are ultimately stay ultimately within the range that we expect to be reasonable given our prior information. Okay, and this picture becomes even more extreme when we definitely basically leave the realm of large sample properties and the central limit theorem. Here we just have a sample size of 10. We again go through the same exercise. We just run this this function with a sample size of 10 and look at the result of the frequentist GLM output and the Stan output. And we see that this bias is even more extreme for our slope coefficient. We have a parameter or point estimate of 1.548, so even larger, due to the fact again that logistic regression tends to be biased for small samples, at least in the classical frequentist framework. Okay, so we have larger bias, and we have also a lot more uncertainty around our estimates. Okay, and so compared to that, if we look at the estimates of our Bayesian model, of course, now with such a small sample size, the parameter tends to get closer to the actual prior mean than the true parameter value. So we're here at 0.59. Remember again, the actual slope coefficient was 0.8, or in the true data generating process it was 0.8, and then our prior distribution was centered around 0.5. So we see here with such a small sample size that this coefficient is more strongly affected by the prior distribution than the underlying data and the likelihood. But nevertheless, basically conditional on specifying a prior that sets a reasonable range for our coefficients, we still, despite the fact that we have such a small data set, we still have a better model for prediction by kind of incorporating this prior information. Okay, so in other words, in basically incorporating prior information and working in a Bayesian framework allows us to address some of those issues that we have in the context of frequentist classical logistic regression with small samples. Okay, because there we encounter increasing bias if our sample size is becoming too small. Okay, so this is all for now about priors in the logistic regression framework. We'll talk a little bit more in the upcoming weeks about informative priors later on in the semester. But for now, we'll leave it at that. Now we're going to move on interpretation and how to actually visualize results from a logistic regression model. And so that's going to be the topic for the next video.